Let's start. This is the second last lecture of the course, and the title is Game Theoretical Agent-Based Models. So I'll go through all the terms, I'll tell you what agent-based models are, but I'll also go into basic game theory. And for me personally, I didn't know anything about game theory when I started the fellowship, so this is something I read up partly just to give this lecture. So what we want to do in general, all of us right in science, is we want to understand the world, and this is a puzzle with different pieces. So the first piece is the data, and in order to understand the data, we need to collaborate. As a statistician, we would collaborate with scientists, physicists, biologists, engineers to really access what it contains. And then the next puzzle piece is statistics. And as you have seen, this week, you can, just with these two puzzle pieces, do a lot of interesting approaches, data-driven approaches like neural networks. But in many cases, you want to add a third puzzle piece, scientific causal models. So you have seen Aidan presented that, right? You want to describe your system with PDEs, for instance, and Sim did the same. You describe the system first from a physics perspective, and then you use that, you make predictions, and you compare your model to the data, and then you see what parameter values work, and what that gives you is you can understand the dynamics and the mechanisms that underlie the data. And now how do you make this comparison? This could be MCMC or HMCs. Aidan talked about some methods. John discussed some methods. And I'm completely going to ignore this part, the inference part. I'm only interested in this lecture in the last puzzle piece. So you had the previous case, it was PDEs as this kind of puzzle piece. And in this lecture, it's agent-based models. So what are agent-based models? So it's a kind of model where you're looking at individuals or entities that follow a set of deterministic rules. So in my research, I have, for instance, looked at mathematical oncology, so tumors. And tumors you can understand with PDEs. You can think of it as a fluid that diffuses through the brain, right? But you could also think of a tumor as something that is built up of tumor cells. And then every tumor cell would be your agent. And so this follows a set of rules. A tumor cell will die, it will migrate or divide. And to write down these rules, you would need to talk to a medical biologist to write down the probabilities. And then what you do is you follow the agent at every time step, see what they do. And by every time, so you can hear there's also this element of finite time steps, like Aidan talked about for differential equations, right? And so you just want to know what does this individual agent do, and you follow them. But of course, a tumor is not one cell, it's thousands or millions or billions of cells. So you follow all of them individually at every time step. And some of them here in two different colors to show that some of them follow one set of rules, and some of them have a mutation, so they follow a slightly different set of rules. So you have different types of agents that interact, and that means it gives you the ability to describe the system on a microscopic level, either cell basis, and then you can step back and say on a macroscopic level, how do tumors behave? And so you could look at the tumor volumes, just the sum of cells. And this is an emergent property, just falls out of your agent-based model. You didn't put it in, right? It's just something that is what is the overall summed up behavior of the population, given that you only looked at individuals. And so maybe you could describe this then with a PDE or something, and you would like the agent-based model to give you the same result in the end as the PDE, right? And you can then use that to constrain the underlying microscopic mechanisms. And so during the fellowship, I also moved into the social sciences. And in social science, the individuals in this kind of models would be people. And there are a lot of, in terms of how you program it, there are a lot of things that are the same. But in terms of people are very different from physical phenomena in the sense that they understand the rules they play by. So if you, for instance, if you make a prediction about the weather doesn't care. But if you make a prediction about what people do, they might say, and change their behavior, right? So this is a very different type of behavior. And that means the issue is here you have rational decision makers, and this is where game theory comes in. And so you have people that follow a set of strategies and make these into rational decisions. And I read two of these books, are two of the books I read for this lecture. The left one is on classical game theory. That's where I will start out. And then we're going to move into, in the second half of the lecture, we're going to move into evolutionary game theory, and I'm going to talk about how this applies in nature. And so in the first part of the lecture, it will mostly be concepts, and in the second half of the paper, it will be research papers for you then to, since your task is to make this into posters, right? So first of all, what do I mean by all of this? What is a rational decision maker? A rational decision maker player, what we assume is it's somebody who knows what they can do. They know all the possible actions they can take in the game. They know what all the possible outcomes of those actions are. And they know what preferences they have for these outcomes. And they also have, to start with, we'll assume they have complete information about the game. This is a game like chess, for instance. In chess, you know exactly what every move can do. You know what all your possible moves are. You know what your preferences are. You want to put the other one checkmate. And you know everything that the other player knows as well. And you know that their objective is to put you checkmate. So there's nothing hidden. And as we go on, in principle, you don't know what they will do, so what they will move. But you can compute the probabilities for everything they are going to do in the next step, in principle, if you were a computer. And so now you might complain and say this is not how humans actually behave. This sounds more like how a computer plays chess, and that's true. As we will go on, we will see we don't need these assumptions, so we'll get rid of them one by one. In addition to that, you also know that this is kind of how you should make a decision, right? If you're going to make a decision, what you should do is write down all your options, write down all your outcomes and all your preferences, and then you should make a decision based on that. So in this, you can see this as the ideal decision maker. If you're playing a game for something, so there's a payoff, and that means basically, that just means when you make a decision, you need to attribute a kind of function to it that says what is the outcome you like and how do you rank this. And so to take a very kind of a low-level example, but it's a decision, imagine I make you choose a dessert, then the kind of payoff function here would be that you like cake more than you like ice cream, and you like that more than you like cookies. And if you're rational, there are certain things about this. For instance, this set is complete. I cannot give you a dessert and you say, I don't know. And also, it's transitive. So if you like cake more than you like ice cream, and you like ice cream more than you like cookies, you obviously like cake more than you like cookies. Otherwise, you are irrational, right, in this setup. Players then are playing to maximize their payoff. What that just means is, if I ask you to choose a dessert, you take cake, because it's the one you like the most. This might be a bit hard to see how do you actually quantify this. Another example would be a company, right? Just assume a company, if let's just say the only thing they want to do is to maximize their profit. So now you have just the amount of profit they make, that you can write down. If you can write down, say, a differential equation for their income and for how much they spend, you just have to find out how to maximize that function. That's a lot of economical model would work like that. It's just in the real world, it's more complicated. So just as a short example of that, here is a paper from 2000 where the idea was that you had a kindergarten and the parents collected their kids a bit late, and that meant the kindergartner had to stay a bit longer. And so the issue was, they said, okay, if you collect your child late, for every minute you come late, we will fine you. And they hoped then that by being fined, they would come earlier, because the payoff of these parents would be not to waste money. And as time then goes on, you find that the group that is fined comes later and later, while the control group is only 10 minutes late. And the reason is, of course, that as a parent, you came early to collect your child because you felt guilty about letting the kindergartner wait. Now you're paying the kindergartner, so you don't feel guilty anymore. And so the payoff function is not just money. Right? So if you actually have to write it down for real people, it's a bit more complicated. Okay, so these were two of the concepts. This is the first game. We're not going to play this one, I'm just going to explain it, and then later we're going to play some of the games. Okay, so often you will see that in these games you have two players, so player 1 and player 2 here, and this is called the prisoner dilemma. You're going to find this in basically all the books on game theory. And And the narrative behind this is you have committed a crime, you're a suspect, the police brings you in, and they put you in one interrogation room, they put another person that has also committed the crime in another interrogation room. And they can put you in prison, and they can give you 2 years of prison each. And so, however, they know you have done more than they can actually pin you down on. So what they want to do now is they want to they strike a deal with you. If you are willing to think on the other one, so snitch on the other person, you only get 1 year in prison and they get 5. If they think on you and you keep your mouth shut, you get 5 years in prison and they get 1. But if you both snitch on each other, you both get 4 years in prison. Now, so basically in this matrix, you can see there's player 1 has a decision, do they want to cooperate, so keep their mouth shut, or defect, so snitch on the other one. And then there's in the upper cell, there are 2 numbers, -2, because you don't want to be in prison, so -2 years in prison. And that the first one is player 1's payoff, and the second one is player 2's payoff, right? So what are you now going to do? And to find out this, you say, well, imagine that you don't know what the other player does because the other player is in another room. Imagine they cooperate. You want to maximize your own payoff. Well, the best thing you could possibly do would be to snitch, because then you only get 1 year in prison. Imagine now that they snitch. Well, the best thing you could do would be to snitch as well, because then you only get 4 years in prison. So the logical, rational thing to do would be that both of you defect. And so you end up in this situation, which is called the Nash equilibrium. It's the situation where none of you can improve your situation by changing the strategy. And this, of course, seems stupid, because both of them, even we said these were the most rational kind of people you could get, because this would have been a better solution. This is a Pareto optimal solution, the socially best solution. But you're not taking that because it's not in your payoff. It's not what you're interested in. If you changed your payoff function and you said, well, people actually care about the other person in the other room, then the game would change. But within this game, we have assumed, so to speak, to begin with, that these are egocentric, then this would be the outcome. We will see how we can deal with this. And then one more model, and then we're ready for our own game. So this is just to show you that you can have these kind of very simple, let's say, or not simple, but binary decisions can go into research papers. So this is about fisheries, so areas of the sea where you can go fishing, right? And you want to protect these. So you want to say, in this area, you cannot fish. And then you have a set of players, a set of fishermen. There are, let's say, 100 of these. Each player is called I, and we now draw their decisions as a decision tree. And they can now either decide to join the scheme and protect the fish. In that case, they don't fish in a certain area, so they get less fish, only FY fish. But if they do that, you give them a bonus, so to compensate for the amount of fish they couldn't fish. On the other hand, if they ditch you and they don't go into this scheme, then they will catch more fish, Fn. So now the question is, what are they going to do? And this, by the way, under the hood, it's an agent-based model. So you have a set of agents, computer simulation with agents here, that talk to each other as well. So the way they find out what to do in the next time step, because they have to make the decision at, like say, on a daily basis, is they go and talk to the other fishermen, find out how much did you catch last time, and if they find out that everybody is doing better when they take the bonus, for instance, they will go and take the bonus and protect the area. So there's a social learning behind. And if you now simulate this, the result you get is something like this. So the number of fishermen that join the scheme shoot up, and then it kind of falls down and plateaus. And the reason for this is you're also simulating the fish. If nobody goes and fish there, the fish population recovers. When the fish population recovers, going and fishing there is more profitable. And then at some point, people will find out that it's better to not join a conservation scheme and go fishing than it is to take the bonus and protect it. And so if, given that these were your assumptions about how people reacted, and that the only incentive was how much profit they were making from fishing, then this would be the kind of behavior you would obtain. Okay. So basically, from this slide, you just have to take. We show this sometimes with decision trees, and so now this is the. Yes, please.
This also depends on the bonus, yeah.
yeah, so basically what you could get out of this is how much of a bonus do you need to pay for people to protect to a certain extent, right? So yes, you're right, it depends on the bonus. Okay, this is the first game for you. It's called the Centipede game. It's a repetitive game, and there are 2 players. So up here it says 1, 2, 1, 2, 1, 2, 1, 2. And there are at every kind of forking here, there are 2 decisions. You can either decide to continue the game or you can decide to stop the game. And so the narrative behind this is, imagine I come and offer you £1 each, you and player 2. If you decide to continue, it's now player 2's turn. They can decide now to let you go without any money, take £3 and run, or they can decide to continue the game. If they continue a game, you both get £2. And so it goes up all the way to both of you getting £50. If you just both decide to continue at every single step, you end up with £50. And so the way this is written is, there's a parenthesis with 2 numbers. The first number is your payoff. The second number is the other player's payoff. Here you are player 1. Okay? If you are player 1, and we are just in round number 1 where I offer you £1, £1, what would you do? Would you say, I take the £1, stop the game, and it's fine? Or would you end up with saying, oh, no, I continue the game because I want to go for the £50? I'll give you 20 seconds. You can talk to your neighbor, and then we are going to just vote for it.
Is this the one where they're acting rationally?
Your player, your opponent is a rational player, yes.
I would continue, I don't care what they do.
Yeah.
It's just,
Oh, it gets irrational.
I don't really care about the they get it. I'm like, hey, I'll take your £3, asshole. Great job.
Times 100.
It's really fun.
Okay, so if you think, this is just very, very low tech, if you think that you would continue the game, put up your hand. So the thing you should most definitely do, if you are rational players, you should stop immediately. And the reason why you should stop immediately is, let's look at the other end of the game. In the other end of the game, the last turn is the turn of player 2. Player 2 is rational. Player 2 can now get £50, or stop the game and get £51. £51 is much better than £50, so they will stop. You are a rational player, so you know that. If they stop in the last round, you only get £48. So if you stop in the second last round, you get 49. 49 is better than 48. If they know that, so they're going to stop in the third last round because £50 is better than £49. And so it goes all the way down. So basically at the beginning, if you continue, they will think, oh, that wasn't very smart, take the £3 and run. And if you might say, and not all of you voted for stopping the game, of course here the setup is that there's an advantage in being the last one who has to make a move, and there are other games where your first mover advantages and so on. Now, not all of you decided to do this, and if you actually ask real people what they want to do, it turns out that real people continue the game. And we will talk about why this is the case. If you ask chess grandmasters to play the game, chess grandmasters will stop immediately, because chess grandmasters are trained in playing chess. It's a rational game, so they look through this and stop the game. We will kind of talk about how we can make this more like what real people do. Another thing is maybe your payoff function is just not like that. Maybe you care about whether the other player gets £50 as well. And who says that your payoff function has to be the same as the other one? Similarly, who says that your payoff function is the same all the time? I mean, you might be in one mood or you might be in another mood. So there's an agent-based model from a research paper just on this to illustrate this point. So what they say in this paper is basically that if you say you eat lunch, so that then you're hungry, you eat lunch, that has a high payoff. Once you have eaten lunch, eating lunch again and again and again doesn't really have much of a payoff. So your payoff of activities is a function of time. depending on what you did previously. So all they do here is they take an agent, they give it a set of payoff functions that are a function of time, and then they try to see what would the calendar of this agent look like. And so the one here, the column 1, is Monday. And so they say, what does the agent do? Well, the agent gets up, it runs to work, it eats, it works, it eats, it works, it gets home, it eats dinner, it goes to sleep. And then the next day, because this agent has no alarm clock, it ends up with getting up earlier. So now it's not so desperate to get to work anymore, and it finds the time to have lunch, because the payoff of having lunch is higher than the payoff of going to work. So you can get very realistic behaviors in the terms of this could be a real human's kind of weekly schedule by just making time-dependent payoff functions. Okay. Now, one thing you could do, so the problem with this centipede game was that you had a game that repeated over and over, and then there was an end to the game, and that introduced an asymmetry. You could also have an infinitely repeated game, so it just goes on for forever. And so imagine there's an infinitely repeated prisoner's dilemma. So you go through the interrogation, you go to prison for a certain number of years, and when you came out of prison, there will be another prisoner's dilemma for forever. And now imagine that the person you're playing with keeps a grudge. So the person you're playing with will be happy to help you the first time, will cooperate with you the first time, but if you ever trick them and kind of cheat them, right, finger them, then they will never help you again. And that is not an irrational behavior, it just means that revenge is a very big part of their payoff function. Now what should you do? There are two things you could do. Either you, in the first round, you know they will cooperate, so you can get only 1 year in prison the first time, and then the only thing you have to pay for that is for the rest of eternity you go 4 years in prison forever, because you're going to end up in the national equilibrium, whatever you do. Or you can take 2 years in prison the first time, and then you can do that forever and overall get less. And this depends a bit upon how you see the future. So there's an experiment with kids from the 70s, just to illustrate what I mean, where there's a psychologist that goes into a set of kids and it says, here's a marshmallow. If I have to leave the room now. If the marshmallow is still there when I come back, you get a second one. But if you've eaten it already, you don't. And now the kid has to decide whether the gratification of eating the marshmallow now is stronger than this abstract concept of a marshmallow it hasn't seen. And so there's a discount factor. The not real marshmallow is not as good as the real marshmallow, and it's in the future. Who cares about the future, right? And so if you write down the payoff for the prisoner dilemma game, in this case, your expected payoff is the payoff of playing a round, plus the payoff of the next round times how much you care about the next round. Plus, if for the round that comes even further in the future, you have another discount factor because it's either further away, right? And so you get an infinite series where you have a discount factor that depends on how much you care about the future. There are, of course, this is a very human thing to do, that you don't care as much about the future as now. Of course, there's some things where this is actually really the case, like money. Money is not really worth as much in the future as it is now due to inflation. But this kind of game is different in the sense that if you don't care about the future at all, so if delta is 0, so you only play for now, you're going to eat the marshmallow immediately, then you play a very different game than if you play for the future. And that means that if you add infinite players to the game changes. And so states, for instance, or law firms or companies are infinite players because they play for tomorrow as well. So if you have an interaction between two people and you put a law firm in between, the law firm will regulate because they care about the reputation of the law firm, not just about this one transaction. Also, of course, if you only care about your profit, it will not be sustainable, your strategy overall. And another interesting aspect about this is infinite games are like potential future games. So if you have an interaction with a person and there's a probability that you interact with the person again, then this is mathematically just like an infinite game in the sense that you can think of this delta here as the probability of meeting the person again. So if you only encounter a person once, you will play a different game than if you keep. So if it's a social relation, you will probably meet again tomorrow. Okay, and that was the last part of the introduction to the first part of classical game theory, and now we're going to drop one of the assumptions. So as I said, to start with, I assume that you know everything about the game like in chess. This is not true for all games. So for instance, in poker, you don't know everything about the game. And it's not in the sense that you don't know what cards they have. That's one thing. What you don't know is how risk-averse they are. You don't know what strategy they play by. You don't know. This kind of information is kept private, and in poker, very private, right? Because this is the part of the game. There are real-world things that are the same, are kind of not games, but auctions, for instance, are games of incomplete information. If you actually knew how much everybody valued a piece of furniture or something that you're selling on an auction, there's no need to have an auction. You just give it to the one that values it the most. But people, of course, will lie about it or keep it a secret, or they will. Right? So that's why you have an auction. Is an effective way of revealing how much people actually value the game and reveal this private information. Okay, and for that purpose, we will play a game, and it's a bit more complicated game this time. So it takes a bit longer introduction, but I'll ask you later what you want to do. So consider that you are in a committee, and you have to accept or reject a funding proposal. And you are on the committee with one other person, and if you accept the proposal and it's a success, you will be very happy, and so your payoff is the success Q of this probability for success Q of this proposal. If you reject it, and or if it's rejected and you think it will fail, you will also be happy. And so since Q is the probability of success, you will be as happy as the probability of failure, which must be then 1 minus Q. So just to put in some numbers, assume that it's the probability for success is 60%. Then you have your probability for success, if it's accepted, is 60%. Now it's 0.6 here. Both of you are equally happy about the outcome. Now you can see this matrix is not symmetric entirely. So what also happens here is only if both of you, there are two people on the committee, only if both of you accept the proposal will the proposal be accepted. If even one of you rejects, it will be rejected. Okay? Now, this is a game with complete information. You know everything about the game. Everybody knows everything about the game. And there's no question of what you should do. You want to maximize your payoff, so you accept in this case. And the other person wants to maximize their payoff, so they accept. And now everything is done. Now imagine that you are an expert on one topic and the other committee member is an expert on another topic. So you have some private information of failure that the other person doesn't have. And just because you are not allowed to talk to the other person. So this is information that you keep for yourself when you read the proposal, and you just have to say accept it or not. And so what happens here is, if you have a kind of, let's say, the gut feeling that it will fail, the probability that you have this gut feeling that it will fail, if it actually fails, is P. And the probability that you have the gut feeling for success, if it actually succeeds, is also P. So it's a metric. If you have a gut feeling that it succeeds, but it actually fails, that's the opposite. That's 1 minus P, and the same for success. Now, the other person has exactly the same gut feeling. It's symmetric, completely symmetric, but you don't know what that gut feeling is. And so to show you what I mean by this is that imagine you wanted to compute the probability of success given your gut feeling that it's a failure. You use conditional probability, so that is the same as the probability that there is success, and you have the gut feeling divided with the probability that you have this gut feeling, and you will find that the probability is now lower than Q. Okay? So if you read it and the information you can both understand tells you that it will succeed, and it succeeds with Q, but you have this gut feeling, then the probability will fall a bit below, and you think, it's probably not going to succeed. And now comes the question. I explain the question first, and then I want you to vote. And this time with private information, so nobody talks to anybody, right? So the question is, imagine your gut feeling for failure is so strong that you think it will fail. So the probability for success is now lower than 50%. If you did not have your gut feeling, the probability should have been over 50%. So you would initially have thought it succeeded, but with your gut feeling you don't think it succeeds anymore. You cannot talk to the other person, but you are asked to vote. Should you accept it based on your gut feeling, or should you reject? And what I would like you to do is to take your phone and either scan the QR code, or you can go in on slido.com and vote. So there's another game going on, right? It sounds very much like rejecting. Is this a bluff, or is it a double bluff from my side? I thought I checked yesterday from Mohammed says, and I thought I has to have the worst phone in the room. So I thought if mine works, but okay. Okay, did people vote? Kind of. Did some people vote? Okay, let's see what you said. So most of you would accept. A handful would reject, and that's the correct answer. You should definitely accept. And the reason why you should accept is that you have to condition the probability for success on the other person too. So if you have a gut feeling of failure, the other person might also have a gut feeling of failure. In that case, we can all agree you should just drop it, right? But you cannot communicate with them. Similarly, if you both agree that it will succeed, well, then it will most probably succeed, and you will also be fine by just doing whatever your gut feeling says. But the interesting cases are these asymmetric ones, where you feel it succeeds and the other one feels it fails, or they think it fails and you think it will succeed. And so what you actually care about is the probability of success given that you think it fails and your belief that the other person thinks it's a success. That would be the interesting case where there's an asymmetry. And if you put in your numbers here, it turns out that the probability is just Q. What does that mean? It means their enthusiasm cancels your kind of feeling of failure. And now why is that interesting? That's interesting because the game is asymmetrical. The proposal is only accepted if both of you accept. And now imagine that the other person always goes with their gut feeling. If they feel like rejecting, they will reject. So let's say we are in the case where they feel they should reject and you also feel you should reject. Well, in that case, it doesn't matter what you do because they already rejected, and so you can just as well accept. If they feel that they should accept it and you feel you should reject it, you should accept it because we just found out that your feeling of rejecting it or failure is compensated or cancelled with their feeling of success. So actually the probability of success is still Q. So in that case you should definitely also accept. And of course if both of you feel like accepting, you should accept. So the thing is here, you can always accept because either it doesn't matter or it's the right thing to do. And this then, of course, it's not just you who has to do that, it's also the other person who has to do that. And that means that this is actually a Nash equilibrium. Of course, it means that the case where both of you rejects then falls under the table, but that's what you have to live with. If you cannot communicate with the other committee member, just ignore your gut feeling, is the kind of setup here.
Don't you always ignore your gut feeling?
What I mean by gut feeling here is a private information that you only have for yourself.
Yeah, but the private information is never useful in this example, right?
The private information is never useful in this example. If you, for instance...
because if Q is greater than R,
yeah.
all options but accept give you less.
So basically you have what is the probability of success? It's Q. right?
Yeah, so you ignore P.
So you ignore P here, right?
Yeah.
And the reason why but what you actually, to compute that, what you had to do is you had to see that you had more information than just what went into Q. So you have a set of private information, and if you take that into account, it would lower the probability of success. It's not actually Q, that Q is a mistake, other than the fact then that the other person in the room also has a gut feeling, and if they thought it succeeded, it turns out in this particular example to be symmetric, and so you can ignore it because P goes out. So in this game you should, by the setup of the game, not in the real world scenario. If you're an expert in something and you read and say, all the statistics here doesn't work out, you shouldn't say, well, the other person is a biologist, so maybe they don't know, or maybe they know, but let me just ignore that, and you're an expert on this. That should not be the case, right? But in this particular setup of this game where it's some kind of gut feeling, you should just accept it and ignore your private information. Yes?
But if your peer doesn't always go with their intuition,
Yeah.
then this no longer holds.
Yeah, so this is the argument for, that's the argument for what you should do. Now the other person makes the same argument, right? So the other person is also always going to accept, and now you run into a problem. Now you run into the problem, you're fine in this box, because you're fine if one of you feels like rejecting because they cancel each other. You're fine if both of you want to accept, because you should just accept. You're no longer fine if both of you feel like rejecting, but that's just what you have to live with. It's the Nash equilibrium. It's like with the prisoner dilemma. You both decide to go longer in prison, although that's a bad choice. So it's not necessarily that means that it's an optimal choice, it's just the most rational choice.
But we arrived at we all accept by the assumption that your peer would always go with their intuition, right?
Yes, so so if your peer always go with your intuition, that would be the best thing to do. And I'm just telling you, and I'm aware I didn't prove that. I'm just telling you that the other person should do the same. And if the other person does the same, you can show that that also turns out to be a Nash equilibrium. And I'm not saying this is the perfect solution. It just turns out to be the most rational thing to do. Okay, I am far faster than I thought. I thought of putting a break here. Would you like a 10 minutes break? Okay, should we start again? So in the previous example, there were some conditional probabilities, and so if I tell you that there are conditional probabilities, the fact that there's a game with incomplete information is a Bayesian game might not kind of be surprising. In somewhere behind the math of how you do this, Bayes' law will be hiding, right? But it's not just the fact that you have probabilities involved. So for instance, rock, paper, scissors has probability involved, so you don't know what the other person chooses. And the best strategy we will signify here with sigma, is that you play each of them with 1/3. This is not a game with incomplete information, because there's nothing that is hidden to you here about the game. You can both agree, two rational players, two chess grandmasters sit down, they agree. What you should just do is randomly pick one of them with a probability of 1/3. That's the Nash equilibrium strategy that everybody can agree on. That it's because, again, what is the Nash equilibrium strategy? It means you could choose another strategy. Let's say one of you always plays rock, but then the other person could change their strategy. So this is the strategy. If you both play 1/3 for all of them, there's no way you can change your strategy and get a better result. So in that sense, it's the Nash equilibrium, right? So this is not the thing we are looking at. What we think about is this incomplete information means there's something that is private to the other person, like in poker. You don't know what is the actual payoff function, what's the personality of the other person, what's their payoff function. So for instance, in negotiations, that's a game, and there's negotiation games, right? You might pretend to be tougher than you are, and that you're willing to risk things that you're not really willing to risk, because you're signaling that you have a different payoff function that you really have, hoping that that will make the other person believe in your bluff and change their strategy. So basically the question is what you see really what is true. That's what you don't know about Bayesian games. And so just as an example from biology, on the left here you have a bee, on the right here you have a fly. This fly looks a lot like a bee, and it wants to look tough, so that it's not eaten by birds, but in reality it's just a fly. And so this is exactly the kind of thing we are having, that some players will pretend to be something else. And so there's a large part of this that are so-called reputation games, and there's a very nice paper recently by Enslin et al. And if you were to make a poster, I think this is a nice starting point for a poster. And basically what this is an agent-based model. So here you have 4 agents, a yellow one, a red one, a blue one, and a green one. And what they really care about is how honest the other players perceive them to be, or how honest they feel themselves. So there's the self-esteem about their honesty and how other people see them. That's what they actually care about. That's their payoff function, as well as their reputation. And it's also the only thing these agents talk about. So, yeah. So basically, the yellow agent here talks to red about how honest yellow is, because it wants to convince red about the honesty of yellow, right? Green talks to red about blue. If green likes blue, then it's going to talk very well of blue, and if it doesn't like blue, it's going to trash blue, right? And that means, of course, that the agents to some extent might exaggerate or lie, right? So this is a game where you try to, ironically, you try to seem more honest by lying, right? And so now that if you're trying to boost your reputation in this way, there are questions you have to ask yourself, right? Who do I talk to? Do I only talk to friends, or do I only talk to enemies, or do I only talk to liars, or do I only talk to people who tell the truth? What do I talk about? Do I only talk about myself? Do I only talk about enemies? Do I only talk about friends? And how much should I lie? Should I go out vividly exaggerating everything, or should I just lie a bit so that it seems more honest? But then I can kind of boost my reputation kind of in small steps, right? Now you know that everybody else is lying, so to some extent, they kind of tell the truth. Should you believe what the other people say? And in order to make any of these decisions, you also need to know, or you need to have a belief of what the other people believe. So if I need to go around lying about how honest I am, I need to know whether you would probably believe my lie, so I have to boost my lie compared to my belief of your belief in my honesty. So you can hear this is getting a bit complicated, but that means there's a probability distribution associated with your belief of the other belief. There's a probability distribution associated with what kind of statements you perceive as a lie, and so on. So there are probability distributions and 3 parameters here in the model, and you update this behind here with Bayes' law. And so if you were, for instance, doing a poster on this, you could dive into the math. It's a bit a longer paper, it's like 50 pages or so, but the math is well explained in the appendix. And so just to show you what the outcome of this, there are many examples in this paper, but just one. And I know this is a very busy graph, but it's a very nice paper. Here, the dashed line here is the real honesty of the red agent, and it's 0.14. It means that the red agent only tells the truth 14% of the time. It lies quite a lot. The fat red line is the self-perception of red. So red doesn't know how much it lies. It goes around lying, and then it kind of gets a picture of itself. Oh, I lie a lot. But this is something it has to find out over time about itself. And these dashed lines that are kind of hard to distinguish, but just the red lines here is the perception by the others, right? So everybody finds out that the red one is a liar. Even red one figures out that it lies all the time.
So I have a question.
Yeah, please.
So you said like if I'm one of the agents, right, then I don't know my propensity to lie.
Yeah.
But that's not really true, right? Because when I'm lying, I'm obviously drawing from some distribution where every instance I decide to lie or decide to not lie. Are you saying that I don't know my distribution?
Yeah, you don't know. So there's a parameter associated with this. This is this 0.14. You don't know your own one.
So I have a propensity to lie, but I don't know that distribution. And this game is telling me that I have a 14% chance of lying.
Yeah, so basically what happens here is that the agents can do two things. If they lie, there's a certain probability, unless they are, I don't know what they call them, but let's imagine there's a psychopath. So there are some interesting non-ordinary agents in this game as well, not in this particular one. But the psychopath, for instance, just lies outright and is happy with that. All the other agents have a certain probability of blushing. So if they blush, they kind of give away, yes, I actually lied here. And that the other ones can observe and say, that was a lie because you blushed. And they themselves realize they blushed, right?
But how do the other agents know that this was a lie?
So the other agents know this is a lie by two things. Either you blush, then it's obviously that you lied, or they have to evaluate whether it's a lie. So if you think, for instance, that if Red says, I'm truthful all the time, and your prior on Red is that Red only tells the truth 20% of the time, you're going to say this is a very unlikely truth. And so you're going to rank that this statement by probabilities, and then you're going to update basically you're going to evaluate what is the probability of this statement to be true or not, and then you have to make a binary decision: is it a lie or is it true? And then you update your belief or your probability distribution of that agent according to that, and said, okay, this one time they told a lie, so I'm going to assume they lie a bit more often. And at the same time, you have another set of sensors. So it's a bit more complicated. You have another sensitivity. So basically, you are looking for what kind of statements do you hear, and what is a normal way of making a statement. So if everybody goes around exaggerating and saying that they are far more honest than they are, you would get used to just saying, okay, that's just how people talk. So you have an extra kind of buffer, and if everybody just lies a lot, you're not going to be as impressed about their statements, because you think, oh well, they can go in either one direction, and the truth is a very broad concept. If everybody tells the truth, you will have a very narrow prior on this. You would say, well, if it deviates just a bit from what I think, well, probably it's a lie. So there's a lot going on in the background here, but basically that you either compare what they say to what you already think, or you see whether they give away that they're lying. That's the two options.
What are these different lines?
Yes. So for the red one, the dashed line is the truth.
So either there is an obvious signal, or it's based on your prior.
Yes, either it's an observed signal, or it's based on the statements or the signal you're getting and your prior. Yes.
I see. Okay.
And so Michaela asked what these lines are. So the dashed line is the truth. The fat red line is the self-perception, and the thin lines are the perceptions by the others. So if you look at the black one instead, there's a dashed line, that's the ground truth. The fat line is the self-perception. So black is nearly always telling the truth. It thinks it's nearly always telling the truth, but the other ones are down here, by the way. So nobody else thinks that black is telling the truth. And this is actually a social phenomenon that you observe, the so-called the Cassandra effect, that ironically the most honest person in the room is perceived as being less honest than, say, the one that is kind of in the middle range of telling the truth, because you have this liar down here. So the liar is destroying the reputation of the black one, even though the others know that it's a liar. So this is one of these emergent properties. They don't put it into the model, it just falls out of how they...
And like, as time goes on, I guess it doesn't get back up at some point.
No, so this is kind of, I mean, the simulation stop here, but I mean, it converges to this. But you can see that there's also some kind of murky colors, right? So if you rerun the simulation, it's an agent-based model with very few agents, so you don't always get the same exact result. And this is because there are probabilities involved, and so the evaluation based on probabilities. And so sometimes you might accept a statement, and sometimes they will have chosen to lie a bit less, and you definitely accepted it, and so on. Yeah.
It's like attractive in a sense that, like, when you take the time asymptotic in different runs, it might like end up in a bit different like constellation.
Yeah.
Does it have like some like attractors there in
No, so if you can see how broad these error bars are, so sometimes the strategy might fail, and the others realize that you are a liar, and sometimes you're more successful.
in terms of attractor, I said there should be like this, or there could be these concentration points, like where kind of like canonical solutions, but there are several different ones.
I mean, you can see for the set of runs here, for instance, that it turns out that every time you run it, red gets a very good idea of how honest it is, and that kind of is converging to always the same solution. It's not everywhere, but it's still relatively broad.
Oh, yeah, for that, yeah. Other one is hard to see because one will need to see the distributions.
But for the black ones up here, it's kind of also the same. It knows it's telling the truth. The cyan one here also kind of gets itself more or less right, but it also has a lower self-esteem because of the red one.
Is it because in this particular game, a very honest person sounds the same as somebody who lies all the time? The person who lies all the time is saying, I tell the truth all the time, and they're lying. And someone who's very truthful says, I tell the truth all the time. And they say the same thing, but they're on the opposite ends of the spectrum.
Yeah, and you got the other agents I would say the other agents also got used to statements, as you say, of this type. And the other agents also have contradictory information, right? Because the red might have said something bad about black. So they're all kind of
regress to a mean level of honesty that is because there exists liars.
Because
never say anyone's 100% honest, because they could just be someone who lies 100% of the time. Because it would sound the same.
Yes, I mean, it would kind of, I mean, they communicate differently, the truthful people, right? Because the truthful person is also never going, it's just going to always say exactly what they think, right? And this is actually for the next scenario a rather important one. So in the next scenario, the red one is now a manipulative pathological liar. Pathological liar means they always lie. They never say the truth, ever. Manipulative means they tell the truth in a very specific, or a lie in a very specific way. So the first thing they do is they flatter all the others all the time. So the lies go in a very particular direction. And the other thing that happens is they go for the other liars. So as goes for your question, right? If the best friend of red is going to be cyan, because if red can befriend cyan, and cyan is a bit more exaggerating their statements, they know that cyan will talk well about them. Befriending black doesn't make any sense, because black is just going to say what they think. And black might think well of you, but it's much better to find somebody who thinks well of you and exaggerates. And in this particular scenario, red never tells the truth, but it thinks that it tells the truth half of the time. And everybody else also has a self-esteem that overshadows their real truth. So everybody is getting, thinking that they are more trustworthy than they really are. And another interesting one is that red here, everybody thinks very well of red, although red lies all the time. Even they think better of red than of the other person. So black thinks better of red than of cyan, and cyan thinks better of red than it thinks of black. And this is, so, I mean, you have a boosted self-esteem here. It's not a recommendation for social behavior. This is, again, an emergent phenomena that you might not you would have said, okay, what happens if you put a manipulative liar in a room? And this falls directly out as an emergent property of the model by just running them together. There are others, so basically they have a long list of behaviors where they try to see what happens if you put this kind of people in a room. And then they have a bit of a sidestep, which is propaganda. So in this particular scenario, the only person who talks is red, and the only thing red talks about is itself. And it says that it's not just honest, it's honest beyond the scale. So this is obviously a lie, because you cannot be more honest than 100% of the time. Right? But in the beginning, the response to that is that everybody's perception of red drops. They think, well, red must be lying because it's talking so well of itself, and it's not my perception of red. Right? But as time goes on, suddenly the perception of red shoots up, because the people think, well, that's just how statements are. People just exaggerate like this. It's just the one normal way of talking. And then you suddenly you believe that red must be telling the truth all the time. And then you realize after some more time that red doesn't actually say anything new. The statements are always the same. So you end up thinking, well, maybe this is just how red thinks of itself. It's actually not true. And then you find out that red lies. So if red says, I tell the truth 500% of the time, and then it keeps exaggerating to 1,000, then the propaganda would work, right?
But what's the true honesty of red?
Well, red in principle lies all the time, right? Because it's saying that it's I think it's saying that it has an honesty score of 10 to the 5 or something, which makes no sense because the highest is 1, right? So in that sense, it lies all the time. Okay, so as I say, you can get, this could be one of the papers. If you make a poster, you could take one of this paper and another one or something, put them together, and as you can see, if you put in a bit of Bayesian statistics, you can get very believable human behavior. And so the question is, can you get even more believable human behavior? And so there was a paper from last year where what they did was they made a kind of... Yes?
1 second.
Yes,
So
please.
could I, a little bit of a tangent, but from the previous results, so if there was a good politician and a mediocre corrupt politician, the strategy from the mediocre politician to sabotage the honest politician would be to bribe and bring in even more pathological corrupt politician, and then this dynamics would just work in the favor of the mediocre corrupt politician because the perception of the honest person reduces. Did I get that right?
So in this particular, so you mean what happened here?
Yeah.
Well, what I will say is, within the confines of this particular game, there is a certain dynamics where you can lower the reputation by including a liar, or in the other case. Observe in this case, however, that they also would think worse of you. So the only thing that is boosted in this particular scenario is your self-esteem. You think better of yourself, and everybody thinks better of themselves, but everybody thinks worse of everybody else except for the pathological liar. So it would not necessarily be a vital strategy.
Okay, cool. Thank you.
Welcome. Okay, so in this one they make a kind of sim-like game. In this one, so this is actually from the paper. It looked like this, and so in this game you have a set of avatars, and instead of having a Bayesian model in the head of the avatars, they just put ChatGPT. So the large language model, and so each agent is controlled by a large language model, and they wanted to see what happens then. And so how this works inside is that they perceive or observe the world, so maybe they talk to other agents, or they interact somehow else with the environment, and then they commit this to memory. Then they might retrieve the memory to plan. So this is just like the example before. They already ate lunch. They put that into memory. So if they have to plan the rest of the day, they're not going to eat lunch again. They will adapt their plans to the fact that they've already eaten. And they might reflect on what has happened. So if they meet another agent that tells them something very urgent, they will change their plans based on that. And the reflection process also means that they are going to take their memories, look at their memories, see how the new information fits in, and then store the memory again. So there's a kind of an information compression here. And that means that the agents might forget information in this setup. In the other, I forgot to say that in the other agent-based model, it's the same, by the way. You have your interactions, you looked at the liars, and then in the end, when you have concluded whether they lie or not, there's also a compression of the information. For you don't go around remembering who lied about what. You just remember. So in that sense, that's also very human, right? Also here, you actually forget information. And so what they did in particular was they implanted the idea that the agents should go for and have a Valentine's party into the head of one of these agents, and then this agent goes around, talks about this Valentine party, and plans accordingly. And everybody else plans, and they try to see what happens. If you ask them after a certain time, how was your week and what did you do they give you a believable story afterwards of what their actual behavior was? And then they try to see, is this behavior more or less believable if we take out components? So if we now do not allow the agent to reflect, it becomes slightly less believable and so on. And they even score it compared to a set of human crowd workers who they overall, so what the human crowd workers have to do is they have to watch videos of the agents and then write an essay, and then that is overall not rated as believable as the actual agent in the model, but it kind of gives you a ballpark of what is believable and what is not believable, right? So it's actually comparable to humans writing. It's doing very, very well, right? As I said, you could find that a poster, you could compare this and the other model, for instance, and put it together. I think it's also a very nice paper, and there are things that the agents don't do that are not very human, and they openly say they do silly things, some of the agents, and what things are these that do not work. We could look into that and talk about that, for instance, as well. Okay, let's play another game, and you have seen the game before, but the game changes now. And so, in this game, it's the centipede game, so just like before. And it's now agent 1 and agent 2, that has to play, player 1 and player 2, and it's the same as before. You can either decide to continue the game and you can stop the game. Now there is a new notion here. There's the notion that there exist nice players. So nice players are players who just they just also care about you in the end, so that means that they will always continue the game. They will never end the game early. And if you played a nice player and you were player 1, it would be straightforward what to do. You just continue the game because you know they will always continue the game, right? Now, instead, what we're trying to say is you are player 2. You are not player 1 anymore, you're player 2. And the other player has decided to continue the game. That's the only thing you know. They have decided to continue the game from in the first round. It's now the second round. You also know one thing about the world. You know that there are only 1% of people in the entire world who are nice. You never met the other person before, but 1% of people are nice. 99% of people are strategic players, so chess grandmasters, right? Nothing against chess grandmasters, but you know what I mean. They're strategic players, so either they're rational players or they're rational but nice players, 1%. So what should you do now? Should you stop the game or should you continue the game? You can talk with your neighbor for 20 seconds and then
If the opponent is not nice, is rational?
Yeah, so you don't know the other player? There's a 1% chance they are nice, and a 99% chance that they're rational. That's the only two type of people in the world.
And so you're in X99 currently?
You are currently at, we're counting, basically we are counting down.
Oh, okay.
So X98, so you are now at X97, and the last round is called 1. That's just a notation thing. You will see on the next slide why that is. We just started in the first round, and now it's the second round, and the first time you're allowed to choose. What should you do?
Does player 2 also think 1% of people are nice?
You are rational. You are not nice. You know you're not nice. You're rational.
Do they know you're rational?
The nice player doesn't care.
Nice player doesn't care.
Because they're nice.
One would be rational.
Yeah, the other player knows. The rational player knows that you're a rational player.
Yeah, okay. Feels like a trick question. It's a trick question.
So either
Being nice one doesn't mean they're always nice, right?
If they're rational, then they stop, right? Because that's the same as the game before. So they must be nice.
they have decided to continue in X19, and that's independent of them being nice and rational?
I'm asking questions.
The game. Rational move to stop the game. Playing with this.
Some expectation. 1% potential.
Okay, so let Let's try. If you think you would consider, just like before, we said if you continue a game, put up your hand. So if you would continue a game, you put up your hand. You should most definitely continue the game. And why should you do that? It's because it's now suddenly a reputation game. It's a masquerade. If the other person is rational, they want you to think they're nice. Because if you think they're nice, you will continue the game and they can trick you later, right, when they get more money. So, and you should actually continue the game. As long as it's very far from the end, you can just continue. So for most of the game, it doesn't matter whether they are nice or not. You should just pretend that they are nice. It's in your interest to believe in them because you want to continue. It's in their interest that you believe in them, even if it isn't true. Roughly when there are 12 rounds left, the other person should start getting wary. Because when you get to the last round, you're going to take 51 pounds instead of 50 pounds. So you're going to trick them. And they know that. So the question is, how long can they pull this? Right? That means that they're going to stop early in order to not make you trick them. And you know that, so roughly around round 14, you should start getting wary. Should you now continue or not? And for you, it's easy. You should just flip a coin. And they, if you look at this, so here's the N, and the N is this kind of thing that went, so that's why we counted down with X98. So in the second last round, when it's their last turn to choose, they should most definitely stop the game if they are rational. If they're nice, they should just continue. And you don't know, and the only thing you have is the information that they did continue in the last round. Nice people continue. So the most rational thing to do here is to play that you are somebody else and to pretend that you are a nice player for the other person. That's why they continued, even if they were the chess grandmaster. Okay? Now what we have talked about so far are what individuals should do and when are rational individuals. And now consider just a scenario that you have 3 chess grandmasters that they all go for lunch and they can choose a dessert, A, B, or C. They all have different preferences. So player 1 likes A more than C likes B, 2 likes C more than B than A, and player 3 likes B more than it likes A and more than it likes C. And now there's a deal in the restaurant. They can only choose one type of dessert, so they all have to agree, and they have to do this by majority voting. And the problem now becomes that, let's see, if you offer them, if you went to the table and said, would you like A or would you like C? So would you like cake or would you like cookies? They would say, well, player 1 likes A more than it likes C, so it will choose A. Player 2 likes C more than it would choose A, so it would choose C. And the third player would choose A more than it likes C, so it would choose A. So overall, by majority vote, the group would take dessert A. Similarly, with C, the group would choose C. So apparently, the group likes A more than it likes C, and C more likes B. So the group likes A more than it likes B. But if you actually go and offer them B and A, they choose B by majority vote, because player 1 likes B more, player 2 likes B more, only player 1 likes B less than the rest. So that means that you have a set of rational agents that have to make a decision together, and the population as a whole behaves irrationally. And so generally, if you try to enter populations, it becomes a completely different can of worms. And so now comes this last topic of evolutionary game theory. And so basically, there's another book here by Springer. It's more mathematically minded if you're more interested in the math behind. But what it says here, just to kind of read, because I think you might also be reading what it says on the slide. It says, consider a population with players with different strategies, sigma I. So this is what we call strategies before sigma I, and these are these mixed strategies. You have a probability, you do this with this probability, and you do that with this probability. That's strategies. That they pass to their descendants, and the proportion of individuals using a strategy in the next generation is determined by its payoff, which just means you have animals, for instance, that follow certain strategies, the more successful they are, the more offspring they become, the more of that type of animal there will be in the next generation. So this is just Darwinian kind of evolution, right? And other than the fact that that I said the word strategy, there's nothing that makes this look like game theory, right? There's no, we don't need any rational player. Nobody is thinking about what animals should do. So now we don't even need a rational player anymore, but we're going to find out that there are parallels if we take a look at this. And the question is, how does this system evolve? And if you're interested in how systems evolve, what you're often most interested in is what states are stable. So what will the system converge towards? And you can think of this as there's something called evolutionary stable states, and the idea here is, I write it here as going with the herd. So basically, when is it that if you choose a certain strategy and it's the same strategy that everybody else chooses, and changing your strategy would be detrimental, then that system is definitely stable. If everybody just has to do the same, then then you have a selection for that is the strategy you would go for. And so it's in there are two conditions here. The first one is that basically the way to read this is the payoff of you doing a certain strategy, sigma star, if everybody else does the strategy sigma star, is better than the payoff of you doing a strategy that is different from sigma star, but everybody's doing sigma star. So this is just a Nash equilibrium. You cannot change your strategy because you have to do what everybody else does. The second option is if you find a strategy where it doesn't matter whether you change your strategy, you would be worse off if everybody else did what you do. So basically, if everybody else does what you do now, and everybody changes the strategy, the person that uses the old strategy, the stable strategy, would be better off. I'm going to show you an example of that, but you can, for instance, also think of this not just in, this is within a population where we're just thinking about what individuals do in a population, but you could phrase this instead as in proportions of animals and be interested in, for instance, how many foxes are there? That's one strategy, right? Versus how many rabbits are there? That's another strategy. And then you have these two. What is a stable state? What is a stable number of foxes in your population, right? You can also do it within a population that you have individuals that behave in a pure way differently. So, for instance, vampire bats have to drink blood. And so if they don't drink blood every 2 days or something, they starve to death. And so what they do is they're social animals, so they go to the other bats and ask them for blood. And so the other animals will give them blood. But you can hear this is a kind of a prisoner's dilemma. Because if you give another bat blood, and when you need blood because you didn't find any, they don't give you any, this is not a good strategy, right? So the question is, how do you need to behave for this? For instance, should you always just say no to giving other bats blood, or what is the behavior? And if you're interested what vampire bats do, it's the thing you have met before. It's the grim trigger strategy. So they basically bear a grudge forever. If a bat doesn't give them something, although it would have something, they will remember that bat and never give it blood. And then, for instance, I mean, you can see this is connected to the prisoner dilemma. Another possible poster would be to take the prisoner dilemma and see under what circumstances is what strategy a good strategy, and how does this connect to real-world phenomena. There will be some other papers on the prisoner dilemma later. So one game that you will most definitely meet if you do evolutionary game theory is the so-called hawk and dove game. So a hawk is a bird of prey, right, and a dove is a pigeon. It's actually nothing to do with that, but just imagine it as being two birds here. And a hawk, a bird of prey, is very aggressive, and a dove is non-aggressive. And so basically, imagine you have two animals and there's a food source, and they meet at the food source. And if the animal behaves like a dove, so non-aggressively, and it meets another animal that behaves aggressively, it will just run away and it won't get any food. If it meets another non-aggressive animal, so if a dove meets a dove, it will share the food. If you play hawk and you meet a dove, you will get all the food because the dove runs away. And if you meet another hawk, you will both start fighting, and then one of you will be injured, and either you get the food or you get an injury. And so you get the expected payoff is the food versus the injury you get. And now the question is, if we have a population of animals that are all the same, and instead of this actually being hawks and doves, you can think of it as when should the animal be aggressive? How it just meets another animal. What's the probability that it should decide to become aggressive? In how many percent of the cases should it be aggressive? And in how many percent of the cases should it decide for the opposite strategy and just run away? So what you do is you write down the average payoff function, right? You say what's the, in this case for P, with the payoff of 2 hawks meeting and 2 doves meeting and so on. Now you just want to find the value for P that optimizes this. And so we can do that, and what you end up with is that the stable setup, if you're getting more food than the injury, the answer is obvious. Just be aggressive all the time, because it's a huge payoff of being aggressive. But if the injury is relatively harsh, you should maybe be aggressive only F over C a number of times. Monomorphic just means that every animal is the same. This ESS is the evolutionary stable state, and the NE means that this is also a Nash equilibrium. Now imagine instead of asking this, I'm actually thinking about hawks and doves. So I'm actually thinking about some animals being aggressive and some animals not being aggressive. And so instead of talking about probabilities, strategies, I talk about proportions in a population. So X is the proportion of the number of hawks in the population, and 1 minus X is the proportion of doves. And in that case, you get that the stable solution looks exactly the same, right? And so basically, the theorem that is kind of connected to this is, if you have a setup where you have animals that all behave the same, and that is a symmetric Nash equilibrium, then the population state is a fixed point for the replicator dynamics, and replicator dynamics is just, you write down, this is the setup where you have animals with a pure strategy that then get descendants and go on in this manner. And what does that basically mean? Nash equilibrium was something we saw before, the rational players, right? There's no mention of rational players here, but you get the same state. And basically what that means is that even though you have no rational player, nature behaves as if a chess grandmaster has decided where the stable state should be, right? This is not the whole story, because evolutionary stable states they're not always there, and so on. Other stability criteria, also an interesting poster, by the way. Okay, so if that's true, that nature behaves a bit as if there are rational players at play somewhere, are all the games that you have seen before also in nature? And the answer is yes. So for instance, there's a prisoner dilemma here with viruses. So imagine you're a virus. What you need to do is you infect, in this case, a bacterium, and when you infect a bacterium, you need to produce RNA, and you need to produce protein to make a shell around yourself, to make new viruses. But there's a certain probability that you're not the only virus around. Maybe the bacterium is doubly infected. There's another virus that's already there. It's already making proteins for its own shell. Why bother making yours, right? Just steal the proteins from the other virus. And that means you could defect. So this is basically the prisoner dilemma defect. And what they find in this one is that there are viruses that do that. And this is a very good strategy if you're the only one that does this. And they can write down a payoff matrix like this. And again, if you're doing a poster on this topic, including some of these real phenomena would be very nice. There is rock, paper, scissors. Everybody plays rock, paper, scissors, bacteria or lizards. So for instance, there's a set of lizards where a set of males that have a different set of mating strategies. So basically, the orange males are very aggressive, and they try to get rid of all other males, and they have a flock of females. The yellow ones look a bit like females, and by yellow I mean the neck is yellow. So they behave a bit like females. The orange one is so occupied with the other males that it doesn't realize, so they can sneak in, right? The blue ones are not as strong and aggressive as the orange one, but they are more social. So they kind of go together, and because there are more of them, they're able to spot the yellow ones. So basically, the blue one strategy beats the yellow one beats the orange one, and the orange one beats the blue one. And if you look at the population of males of these lizards, you can write down the payoff, the matrix here, for how the game plays, and it's the same kind of matrix you would get for rock, paper, scissors game. Is just a bit screwed. So when I said in the beginning that there were agent-based models for cancer, but then I said, well, when you enter social sciences, you need game theory, right? And now you can see this isn't entirely true, because cancer cells are hierarchical. That means that there are different types of cancer cells. They mutate, so they change their strategies. They have to change their strategies based on the environment, and they compete with the field because they are interacting with the immune system. So you could phrase the cancer model as a game theoretical setup, right? It's just a matter of language. All these agent-based models you could. Some of them would be very boring games, since the rules are very easy, but you could phrase them as game theoretical ones. Okay. Why agent-based models? Because maybe you would think, well, couldn't I just use, if I have a population of one animal and a population of another animal, couldn't I just use ordinary differential equations or something and then look at the proportions of the animals instead, right? So the example why here is with squirrels in Britain. So you have two types of squirrels in Britain. You have the red squirrels and you have the grey squirrels, and the grey squirrels are much larger than the red squirrel, and so it outcompetes the red squirrel. The grey squirrel, by the way, is an invasive species, and the result of this is that the red squirrel is going extinct. And so this is actually the kind of game we have been looking at so far, in the sense of we just have two strategies and we see which one wins, right? But of course, real strategies in nature mutate, because in principle, this is not the case normally. Normally, you have some kind of arms race between animals and strategies change, and this is much easier in an agent-based model than in a differential equation. But particularly for the squirrels, the other thing is that there's a finite number of squirrels, right? At some point, in a certain area, there will be no more red squirrels. It's extinct. And so when you have one squirrel, the next step is 0 squirrels, not 0.4 squirrels, like in a differential equation. Extinct is extinct. Then there are some spatial features that sometimes one squirrel is in a certain area and therefore only encounters some other squirrels, not all other squirrels. That's very hard to put in a differential equation. You'll see that there's one more paper I'll present on the next slide. The rules that they follow might be stochastic. That's also much easier in an agent-based model, maybe than in a PDE or ODE. And then you have these emergent properties, right? Now you just need to know how an individual squirrel behaves. If you use an ODE, you need to know how the population as a whole reacts. And actually, all of these different things might change the attractor of the game. So I said before that rock, paper, scissors, a lot of animals play rock, paper, scissors, but rock, paper, scissors as it is not an evolutionary stable state. So you can end up with the situation where if you just solve the differential equations, it doesn't look like there's an attractor, but then if you make an agent-based model, there is one, or the other way around. Okay, so just to make you one kind of what did I mean with all this spatial thing? So on the right here, you see we have a grid with pixels. It says zoom in on agent with neighbors, so the black box is the agent. And the green boxes are the neighbors. And it only talks to its neighbors. Now I put in some yellow boxes just to say that are they not neighbors? And the answer is maybe. And I think in the lecture by Nassim, he also talked a bit about, well, you have to choose your grid wisely, and is a squared grid the right thing to do? And so you have to define what you mean by neighbor. But what it is the black pixel can only talk to pixels next to it, whatever that means, whatever pixels you decide are next to it, right? And now the important panel is the one that says B. And what you are having in B is a lot of agents that play the prisoner dilemma. And the gray boxes, The black blobs here are agents that cooperate, because this is one of these evolutionary games where you can change your strategy. And they have all converged to finding out that cooperation is much better than just snitching on each other. And the reason is that they only interact with the local neighbors. And so if the local neighbors are nice and always interact, they never meet, for instance, if they're in the middle of such an island, they never meet anybody who tricks them. So it's okay, and they can establish collaborations, and they can kind of reinforce each other in cooperation is nice. So you have a game where there's no cooperation, it doesn't appear, and the moment you put it in on a spatial kind of pattern and you add a grid, suddenly cooperation naturally emerges. And by the way, that you could add, if you talked on a poster about prisoner dilemma, altruism as something that comes up in nature. Why altruism is a very good strategy. So the kind of helping each other and being a social animal, why that's also an interesting paper. There are also quite a few things on that. Okay, so as the next thing is, why wouldn't you do agent-based models? So there are three reasons. The first one is maybe the data isn't there. If you are modeling everything on a microscopic level, but you haven't actually measured it anywhere, there's no way to find out whether your model is right or not. Maybe it's not where you should invest your energy for different reasons, right? Secondly, there's a paper by Gu and Blackmore where they're basically pointing out that they have a lot of agent-based models in higher education, so how students learn at university, and there are a lot of very nice models, but some of these models do not actually represent how students really learn. So there were people who made the agent-based model, but they didn't consult the experts who could tell them what rules they really needed to put into them. And so maybe agent-based models you will find in literature might not be so valuable sometimes. And then the last thing is that they're computationally very expensive. It's much less expensive to solve a PDE than to solve an agent-based model. And they're also stochastic often, so that just means that if I run an agent-based model, I get one answer. I run the same model with the same settings again, now I get a completely different answer. And if I keep running it, every time I give a different answer. So now I have to run it many, many times to kind of get a feeling of what the agent-based model does, and they were computationally very expensive, and so I have to consider, is this really worth the time or not, in terms of the research question I want to answer. Okay. And the next thing would be to summarize, but I don't want to do this on my own, so instead what I want you to do is to go in on Slido, and I want you to put key terms. And just individual words, like, now I'm going to give you one, but which I shouldn't do, but just something like game theory is a compound. It's okay, it's one word, but try to put it into one word, right? If you cannot read the QR code, you can go on slido.com and just put in the number. You can put as many words as you like. We'll make the word cloud. No, as many words as you like. People, will they have had enough time? Are the people still tired? So let's see what you put. So Nash equilibrium. Is anybody wanting? I mean, there's game theory, rational player. Anybody has a word they would like to paraphrase? For instance, who? want to say anything about previous knowledge, for instance? What was this? Who put that? So previous knowledge is in this kind of private kind of setup or kind of in the game. And we had this game. Aidan also asked. I mean, he said we had this one game where we found out that you had your private information about this committee, and then you should definitely just ignore it. And of course, this is not that you should generally always ignore your private information. Just in this particular game, that was the setup. In the following game, your private information, or in some of the following games, your private information was crucial for your strategy, right? For negotiation or something like that. So your private information can be very, very important. When I have Nash equilibrium as the big take-home message, like that. Okay. So I think that what we did was we looked at what rational players. There were two different types of games: either static games, you play it once, or dynamic games, you play it over and over, and they could either have complete information or incomplete information. And then we saw that not only can you get rid of the amount of information, you can even get rid of the rational player altogether and discuss evolution. And there was this hawks and doves game. And if you want to make a poster, right, you can do it either within one of these categories, would be an option. Another option here, there are some of the posters we talked about. So the first one, the reputation game. The second one is the one with ChatGPT. Then there's one paper here discussing why should you use agent-based models. And just as an example, there's this prisoner dilemma with RNA viruses, which is also an evolutionary game, and you can couple the prisoner. And then if you want to, just to add a bit more, what you could do, for instance, you could look at, there are some packages for code that you could have a look at. For instance, this AgentPy that is in Python, or NetLogo that is not in Python. And this is the first example from AgentPy, and what it is the spread of viruses. And so the agents in this model are humans, individuals that can have a disease, or they can be susceptible to a disease, or they can already have recovered from the disease. And then the question is, how does this evolve? If the agents are living in a certain social network, and I'm not saying, given the time constraints and so on, you have to program anything, but you could, for instance, go into agent.py, look at what examples they have, things I haven't touched upon in the lecture, and see whether there are any of these examples that you would like to dive into, say, virus spread or something like that. And with that, are there any questions? Okay. Then, yes.
So you said with the, like, when you get to populations, they're not acting rationally, but the game is played like the population is rational. When you say they're not playing rationally, is it just the fact that there's a chance they do one thing, or there's a chance they do another?
So what I meant with that is that what I meant with that is, and maybe you're right, I should have explained that differently. So the thing is, if I take a population of non-rational players, like animals, I have, under certain circumstances and so on and so on, you can end up with having a setup where you say, well, that's actually a Nash equilibrium. That's actually how a rational player would have behaved, right? On the other hand, you can take a set of rational players, put them in a room and ask them to do something, and the outcome will be irrational. It's just that that particularly what we were having here was a set of rules for how you should play the game for each player, and then if you're going into populations, you might want to look at other papers, other literature, other aspects of the topic.